So when you find a limit for a rational function, it's not necessarily, oh, we're always going to find the limit when x equals 2, or we're always going to find the limit when x equals 1. It depends on the problem. There are applicable limits that I want you to look for with each problem. So you have to understand where I want you to look, and then you have to know to do that. So first in our notes, we're going to write down the 3 different situations, or the 3 different places where I want you to look for limits. So applicable limits, there are 3 different places we're going to look. The first one is we're going to look for the limit as x approaches negative infinity, and the limit as x approaches positive infinity.
Do you remember all of this Untitled and stuff? Or you just...
Is this from high school?
grabbed it out?
Do you remember that in high school?
I mean, I had a lot of reinforcement over the years.
Somebody breaks something out.
Don't look offended, you should have been talking. Alright, so the first thing that we're going to look for is the limit as x goes to negative infinity. That means that I'm looking at the left side of the graph. I want to see what that left arrow is doing. Okay? So this is the left side of the graph. The left side of the graph. Melissa, can you sit down? The limit as x approaches positive infinity is the right arrow. What is the graph doing at the right side? So your answers for these two are going to come from the slant asymptote or the horizontal asymptote. Every single time to find the answer for these two, it's either going to come from the slant or the horizontal. Okay? So I'm going to write that off to the side. Slant asymptote or horizontal asymptote. As we do some example problems, you're going to see how specific those different situations will make your answers. Okay? We're going to have certain answers for each situation. Okay. The second place that we're going to look for limits in rational functions is at the holes. Are holes real points on the graph? No. So if we think about it, we've got a picture, right? And we have a hole in the picture. So we've always done this, right? When we find the hole in the graph, we find an x coordinate and we find a y coordinate. Are that point, does that x coordinate and y coordinate actually show up on the graph? No, it's a missing space. Okay? So when we find the limit as x approaches the x value of a hole, the limit is always going to equal that y coordinate. The y value that should be there is the y coordinate of the hole. It's not actually there because it's a missing value on the graph. Okay? So we're going to find limits at negative infinity and positive infinity. We're also going to find the limit at the hole. It's nice and easy because it always just equals the y coordinate. That's not hard to find. Okay? It's something that I've made you guys find already. We've already been finding the y coordinate. Alright, the third place you're going to look for limits is at vertical asymptotes. So we need to know our slant or horizontal asymptote. We need to know where the holes are. We need to know the vertical asymptotes. Once we have that information, we can find all of the limits for the problem that are applicable. Alright, so here is our first example. We're going to look at the function y equals 4x minus 16 over x squared minus 16. And we're going to walk ourselves through those 3 pieces. So first, is there a slant asymptote or a horizontal asymptote? There's a horizontal asymptote, right? And the horizontal asymptote is where? Y equals 0. Y equals 0. We got 0 because we know that the degree on top is 1, the degree on the bottom is 2, and since the top is smaller, that means that the horizontal asymptote is at 0. Okay. Now we need to find the holes in the vertical asymptotes. So what do we have to do to the equation? We have to factor it. So if you factor the top, you get 4 as the GCF. Ooh, be careful. If you take out 4, then your leftover is x minus 4. It's not x squared minus 4. This is not difference of squares.
It does look like a little square.
That was a 1. Yeah, that was a 1. All right. On the bottom, we have x squared minus 16. Okay, so what does that tell us about holes or asymptotes? There's a hole at 4. So we have a hole at an x value of 4. So those cancel. Means the hole has an x value of 4. The leftovers would be 4 over x plus 4. So if we want the y coordinate of the hole, it's going to be 4 over 8. Okay? And 4 over 8 is 1/2. Okay. Alright, we also have a vertical asymptote. X equals close. -4. Okay. So that's the only information you need to look at to find your applicable limits. So I'm going to go ahead and write down my limits that I want to find. I need the limit as x approaches negative infinity of the function. I need the limit as x approaches positive infinity of the function. So for the infinities, we're not going to do the left-hand limit and the right-hand limit because you can't come at infinity from the left side or the right side. Infinity is more of like a concept. So this is saying look at the far left side of the graph, look at the far right side of the graph. Okay? Then we have to look at as we come at 4 from the left, as we come at 4 from the right, and what our conclusion is. As we come at -4 from the left, as we come at -4 from the right, and then what our conclusion is for that one. So I'm going to go ahead and write down all of those. Limit as x approaches 4 from the left. The limit as x approaches 4 from the right. And the limit as x approaches 4 just in general as my conclusion. And when you write these down, you really do have to write it that way. This is the shorthand way to write it. If you want to write it out other than that, you need to write the words, the limit as x approaches 4 from the left. The limit as x approaches 4 from the right. You cannot shorthand this anymore and still receive credit. If you shorthand it more, you won't get any points for what you've written. Alright, so these are all the limits that we're doing based off of the whole of the graph. We also have to look at the limit as x approaches -4 from the left, and the limit as x approaches -4 from the right, and then we have to look at our conclusion, what is the limit as x approaches -4. Yes, it's a lot of writing, that's annoying. I feel you. So once you have all those limits written down, we're going to go ahead and graph this. Okay? So I need everyone typing it in. So we got 4x minus 16 over x squared minus 16. I'm making sure that I've got parentheses around the top and parentheses around the bottom. I didn't want it on my ledge anymore.
I thought someone tried to do motion for a
No, they
calculator.
didn't. There's only 15 calculators, not 16. Alright, so there's the graph. So if I look at the left edge of this graph, the left side of the graph is going to get closer to what asymptote? Did everybody type it in?
I'm doing so.
The original function?
Used to do it once.
Yeah, I'm used to doing
Okay. Do we have it? Okay. So the first thing that I'm looking at is I'm looking at the limit as x approaches negative infinity. So that means I'm looking at the far left side of the graph. So as this graph goes left forever, it's getting closer and closer to that horizontal asymptote. So what is the y coordinate? 0. The horizontal asymptote's at 0. If you're getting closer and closer to the horizontal asymptote, that means you're getting closer and closer to 0. As we follow the graph to the right, I'm tracing it, I'm seeing what it does to the right. It's getting closer to that horizontal asymptote, and so it's getting close to a y value of 0. So on our notes, if there is a horizontal asymptote, then the limit as x approaches negative infinity is just going to equal the number that the horizontal asymptote is at. The limit as x approaches positive infinity is going to equal the number that the horizontal asymptote is at. Okay? Does that make sense? So I'm going to write that on my notes. The limit will equal that number. If you have a horizontal asymptote, the limit's going to equal that number. I don't actually even have to look at that on a calculator. I can get that right every single time without a calculator. If there's a horizontal asymptote, guaranteed that's what it's going towards. Okay. All right, then we have the limit at the hole. So remember, when I say the limit, I'm saying what y coordinate is supposed to be there. I'm not asking what y coordinate actually shows up on the graph. I'm just saying what y coordinate is supposed to be there. So if we look at this graph, 1, 2, 3, 4, the hole would have been like right about, I can't draw on top of my calculator, but the hole would have been, right about right here. What y value looks like it's supposed to be there? 1/2, we found it. It's 1/2. So the left-hand limit is going to be 1/2. The right-hand limit is going to be 1/2. The overall limit is going to be 1/2. Because at a hole, the y coordinate of the hole is the value that should have been there. It's the y value that makes sense. So here, we're going to say, at a hole, the limit always equals the y value. Every single time. The limit always equals the y value. Okay. Now we're going to go ahead and look at the vertical asymptote. Alright, so if I look at -4 from the left side, so I'm tracing it from the left, and I'm getting closer and closer and closer to -4, and my pencil is going down forever. What number is down forever? Negative infinity. So as I approach the vertical asymptote from the left, I'm going to negative infinity. As I look at -4 from the right side, my pencil's going up forever. Positive infinity. And did those two things agree with each other? No, so it doesn't exist. So if you are looking for the limits at a vertical asymptote, your answers are either going to be positive or negative infinity because the graph either goes up or down at the asymptote. Okay? So vertical asymptote limits are positive or negative infinity. Okay? And then we still have to check to see if they agree with each other or not. So you have 3 situations, but all 3 of them are very predictable. Okay? I'm going to do one more example because I do want you guys to see what happens if there's a slant instead of a horizontal. Okay? So we're going to do one more example. We have y equals x squared minus 9 over 4x minus 4. Y equals x squared minus 9 over 4x minus 4. Alright, so what do we notice? There's a slant asymptote. The nice thing about finding limits is you don't really care what the slant asymptote is, you just care that you have one. So I'm good. I don't need to know more than that. I've got a slant. Yes. You do if you need to see what the slant is, but for today you don't actually need to know what it is, you just need to know the graph has one. Okay. Alright, so that's done. Now I'm going to do the work to find whether there's holes or vertical asymptotes. So if I factor the top, what do I get? Okay, x minus 3x plus 3. If I factor the bottom, 4 x minus 1. So, is there a hole on this graph? No. Alright, so hole, none. That's nice because it's one less set of limits we have to find. Is there a vertical asymptote?
Yeah.
Yes. It is x equals 1. Okay, so the limits we have to find is we have to do the limit as x approaches negative infinity, and the limit as x approaches positive infinity. For the vertical asymptote, we want to do the limit as x goes to 1 from the left, the limit as x goes to 1 from the right, and then we want to know our overall conclusion.
Not paying attention. What not? Almost feel like
But you don't have to find horizontal.
There's no holes, so we don't have as many limits as last time.
I always think
So, when you look at these, I'm not going to say every single time you have to find this many limits. I'm saying that every single time you approach a problem, you have to consider these 3 things. And you have to find however many limits you need to make those 3 things happen. Okay? So this example, we have less limits to find than the other example because we only had one vertical asymptote and there was no hole. It is possible for me to give you a problem that has 15 vertical asymptotes when you have to find limits for all 15 of them. Am I going to do that? Absolutely not, but it's possible. So there's not a certain number of limits you always have to find. Okay? You just have to do them for all those 3 circumstances. Yep, we're always going to find the first one. Okay. All right, so I'm going to go ahead and graph this. X squared minus 9, 4x minus 4. So it should look like this. If you follow the left side of the graph, you guys see it, we've got our slant asymptote like this. If I follow the slant asymptote is taking my pencil which direction?
Left.
left, and
Down.
down. So what y coordinate, if my pencil follows this forever, what y coordinate am I getting closer to as I go down forever? Negative infinity. So horizontal asymptotes will give you an answer that's a number on problems like this. A slant asymptote is going to give you an infinity because it's pushing the graph up forever or it's pushing it down forever. Okay? So on the left side it slants down, on the right side it slants up. So the right side is going to be positive infinity. Okay? So when you do your slant asymptotes, one is going to be one infinity, the other is going to be the other infinity. If one's positive, the other is guaranteed going to be negative. If the first one's negative, the other one's guaranteed positive. Okay? So on the front of my notes, I'm going to go back and I'm going to say for slant asymptotes, they're always going to be positive and negative infinity, one of each. So if you're finding them for a horizontal asymptote, you're going to get the number of the horizontal asymptote. If it's for a slant asymptote, then you're going to get a positive and a negative infinity, one of each. Okay? Not yet. All right. Now, we have to look at the limits of the vertical asymptote. So, as you look at the vertical asymptote from the left, which way is it going? Positive infinity, it's going up. If you look at the horizontal asymptote from the right, negative infinity.
Does not exist.
Does not exist. You guys have been talking the entire time I went through this. No, I've been watching you. Alright, so on the left side it goes up, on the right side it goes down. Overall it doesn't agree. Doesn't exist. Okay? And that fits with what we were saying about our notes, is that when we look at vertical asymptotes, the limits are always going to be an infinity. Because you're always either going up or down. Okay? Any questions on that? So every time we do these problems, we're looking for those three things. Alright?